Good morning. I am going to go ahead and get started. Today, I'm going to take a look at some data from Clement. It's got some stretched grids in it. I'm going to take a look at what YT currently supports for stretched grids and then see where it might need to be improved. All right, so let's start out here by taking a look at the data. So Clement pointed me at a repository that he has been using in order to snag some of this stuff. Let's take a look. So we've got these different, this is from a file format that he has, that he works on. And it looks to me like it's very fancy. This is a front end that is built as an external package. So very cool, Clement. We are seeing more and more of those lately, although I think we should probably properly announce them at some point. So let me take a look further on down here. So before I get too far in, what I'm actually going to do is I'm going to activate, and I'm going to show what the current support for a semi-structured grid looks like. So we have some confusing terminology in YT that made sense at the time for how we think about different grids. The thing that I want to mention here that we'll start with is that the basic way that we think about grids in YT tends to be focused on how they are structured in terms of their sizes, whether or not those sizes can be described in a functional way, and whether or not those sizes include overlaps at different levels of resolution. So I'm going to create a new notebook and then put my Jupyter Lab over on this screen so we can all see it. I'm going to go ahead and just get started by importing YT. Then let's take a look at the function load semi-structured grid. So we have, come on, tab complete for me. Oh, right, we called it load hexahedral mesh, right. See, there we go. This should allow a semi-structured grid of data to be loaded directly into YT and analyzed as would any others. Now, here's the part where it gets to be a little bit annoying. So a lot of this relies on the notion that the semi-structured grid itself is a special case of a hexahedral mesh. Why did I switch windows? And hexahedral mesh here is in fact processed typically as a set of cell-centered data cell-centered data, where the cell-centered data is organized not necessarily in a hexahedral mesh, but typically in a hexahedral mesh. So the other thing that, what this ends up meaning is that rather than accepting a set of x, y, and z dx's and whatnot, it actually accepts connectivity and coordinates. This can be a little bit frustrating, but we can make it work for our use case. Now I'm going to dive in here into loaders.py so that we can see what it looks like inside. The main thing that we need to recognize here is that it expects connectivity and coordinates data, which I know I just already said. That's a little bit different than what we might be expecting. So we might be expecting to be able to supply dx, dy, dz, or even just x, y, z coordinates along the 3 different axes for a mesh like this. Instead, what we need to supply is we need to supply the number of vertices, and then we need to supply how you construct cubes out of that set of vertices. It's pretty irritating in some ways, but it also allows us to do this in a much more flexible way. So, for instance, it's not required that we have the same number of zones along all dimensions. However, that is more complex than we typically need for standard stretched grid data sets. So let's take a look over here. We have a helper function, and let's see where the helper function got to. It is not there, so let's take a look at stream data structures. Hexahedral connectivity. This defines the cell coordinates and the cell neighbors of a hexahedral mesh for a semi-structured grid. This can be used to specify the connectivity and the coordinates parameters that get fed into load hexahedral mesh. This is what we actually want to use. So let's use it. So if we do yt.hexahedral connectivity, this takes an x, y, and z. So let's come up with some fun x, y, and z values, shall we? Let's import numpy. I'm going to do numpy.random.normal, and we'll do, shoot, I always mess this up. I always forget the specifics of what we need. We'll do location of 0.0 because we're just going to normalize it anyway. So we'll specify size equals, let's do 64. So here's our set of random values. They're distributed normally. We'll say x, y, z is equal to for I in range 3. Let's go ahead and, so now we have 3. We're now going to normalize them. So x equals x minus x dot min divided by x max minus x dot min. Clamp this to our 0 to 1 range. And then we'll do the same with y and z. I'm sure there's a way to edit these things, these cells more efficiently with Jupyter, but I can never remember the keyboard shortcuts there. So if we plot these, let's take a look at what they look. So now what we need is we need to turn these into XYZ values. Oh, this should actually be size equals 60. Oh, size equals 65. Okay. Wait, what? Oh, right. So these are going to be our widths. You know what? Let's make it size equals 65, and then we'll just sort these. So we'll do X sort, Y sort, Z sort. So these will be our left edges and our right edges. So if we do YT dot hexahedral connectivity on X, Y, and Z, it gives us back our coordinates and our connectivity arrays. So now we have a nice random data set that we can use. Let's come up with some values for that data set. Why did I import it as NumPy? Actually, I hate all these cells that I've been re-executing. I'm just going to clear it. Oh, that one's not going to work. So np.random.random, and then we'll just make this 64, 64, 64, because we have 65 edges, which gives us 64 total. So now, load semi-structured mesh, load hexahedral mesh. We'll supply our data. We'll just say density maps onto rand values. Let's see what else we need. We need connectivity, coordinates, the bounding box. Connectivity, coordinates, and then the bounding box. do we need? I don't think we need anything else. Okay, good. So now we've got our in-memory parameter file. It gives a base domain dimensions of 2, which is not correct, but I mean, it probably shouldn't even be printed out for this. So let's take a look at what we get from this. If we look at everything, yeah, we get it back. All right. So now let's do ds.r. Let's slice along the x direction. We'll plot density. And there we have it. Here is our data set. Now it looks like garbage, I know, but that's because it's a bunch of random values. In fact, I think, here, let's do set log all false. Let's see what that looks like. Yeah, there we go. Now it looks like garbage, but differently. So these are our random values, and you can see that we've got a whole bunch, and they're bunched up here in the middle, but this is our slice through our data set with stretched values. So that's not so bad so far, right? Let's take a second to see what else we can do with this. I think we should be able to plot a radius field or something like that. So let's try that. Yeah, there we go. So you can still see what it looks like here, and it's computing the radius from the center. And yeah, that looks like a radius, and it looks like a bunch of stretched grids. There are these areas here where there's overlap from multiple different cells on a single pixel because they aren't aligned with it. That's probably something we should look at a later time. Now let's also do something, let's do dsr everything, and let's do the sum of cell volume. It should work. Yeah, and it does work. So, that works well. Now let's try something else. Let's see if we can load this in. Let me go back up here. I'm actually not sure that this is going to work, but let's give it a shot anyway. We're going to need to modify our x, y, and z's. We're going to change them to r theta phi. So we'll do r equals x.copy. Theta equals y.copy times np.pi. Phi equals z.copy times 2 times np.pi. I think that's the right one. I always have to look it up, but I guess we'll see. Now, let's see, is it coordinate then connectivity? Yeah. So let's go down here, put this all in here. This time our bounding box, we're going to have it start at radius of 0, and then we're going to go up to np.pi here, 2.0 times np.pi. And we'll say chord S, con S for spherical. Now let's see what this does. Geometry equals spherical. So let's see what happens if we slice it at radius of 0.5. Okay. Looks like I might have gotten it wrong. Let's try slicing along one of the other dimensions. Yeah, still not looking quite right. Anybody in the chat? I see I have one viewer. Want to help me remember which order these are supposed to be in? Am I the viewer? I might be the viewer. Let's try slicing along phi. Oh, there we go. I guess that kind of works. Yeah, I think that I must just have the ordering wrong here. So let's say instead. Oh, no, I don't have the ordering wrong. R theta. I mean, I might, but that's not the specific concern here. There we go. Look at that. We got a spherical, semi-structured mesh. I'm going to quick copy this. I mean, it's not great. You can see these little edges here, but I suspect that's some floating point crap that I didn't take care of. There we go. I know Clement actually had a way to fix this that he was working on. Oh, I guess he's the viewer. He's let me know. I didn't want to speak up in chat, but he let me know in Slack. Okay, and yeah, that one looks kind of garbagey. My guess is that there's some... I'm hesitant to speculate on what the specific problem is there, but that one probably needs some work. I wonder what happens if I offset it slightly. Does it still look garbagey? It does. In fact, it doesn't even look that much different garbagey. I'll have to deal with that at a later time. But looks like we're doing okay on some support for that. Now, here's the tricky part about this. These stretched grids, as you'll see, they don't take advantage of several pretty important things that we can use in YT. So specifically, if we take a look at dd, is ds.all-data, you can see we look at dd.I coordinates, and it doesn't work. So if we look at f coordinates, you'll see that does work. And you're probably wondering, why do I care about f coordinates? Okay, so the reason that we care about f coordinates and I coordinates is that this is how we track the position of different things inside our data set. So when we have a chunk or a data object like this, these are our index space coordinates that we utilize for them. So these are the way that we look, how we this is how we look at where things are located with respect to other things in a consistent fashion. This gets used in, for instance, projections. So projections, which is where we do some sort of an integration along one of the index space axes, all rely on the idea that we have a mechanism by which we can compare things. So in very early versions of YT, this was all done on floating point comparisons. If you had two cells that you wanted to see if they overlap for the purposes of a projection, what you did was you checked to see if their centers, their floating point centers, were equal. I'm sure you can all see why that isn't necessarily the best way forward, because of, you're always getting warned, don't do floating point comparisons. Yeah, we shouldn't. So instead what we use is we use an I coordinates. So an I coordinates is an integer-based system for local coordinate, or for global coordinates. So I'm going to show an example with one of our old favorites, load sample isolated galaxy. So if we look at ds.g, we've got our grid, and let's take a look at grid 100. I think there are 100 grids, right? So this grid has some position in space. Let's call it G. So G has a left edge and a right edge. These are in absolute space, but we also want to be able to use them in some sort of an integer space so that we can compare to find out if this grid overlaps with other grids that might be on its same level. And so we have this thing called the get global start index. For patch grid data sets, that means that this is where the upper left edge of that grid starts in an integer coordinate system relative to the grid's level. If we look at level on the grid, it's set to 8. So a couple relationships here. Grid.dds is equal to ds.domain width divided by ds.refineBy raised to grid.level, right? Except we also need to domain dimensions in there. Why are those different? Oh, yeah, DSG. I was using the wrong data set. So these are equal. So what that means is that we have, based on our global start index and our level, the ability to position our grid absolutely. We do that in the reverse in order to compute these index values. All right, where does that get us? What that lets us do is it lets us find anything else. It lets us compute the integer position of each cell inside that grid. Now, it's really important here to note that this is specific to the level. So you'll note that the parent grid of this grid, the numbers look a lot smaller because it's being computed with respect to its level. So let's say we've got dd equals dsg.all-data. We can access dd.iCoordinates, and that gives us the coordinates of every single value in integer positions inside that data object. But that's useless to us without also having the resolution value. So this has the same shape as the first dimension of this, and this tells us how refined is it. Now, that's where things like refineBy come in, but not everything has a constant refineBy, so we actually have relative refinement, and so we can say, what's the relative refinement between level 7 and 8? 2, okay, or what's the relative refinement between levels 0 and 8? And that's actually the way that we should do this. We should do domain dimensions times ds.g.relative refinement 0 to g.level. And it gives us the same value. And that allows us to have like refinement of factor of 2 on level 1 and refinement of factor 8 on level 2 or something like that. So this is also how we do projections. So if I do a projection here, so ds.r, let's do sum along axis equals x of density. It goes out, oh, sorry, ds.g. It goes out and it projects along that axis. Now, if instead I want to project along r, it's going to give us a not implemented error because we don't have I-coordinates. Now, we also don't have iRes, or rather, we have iRes, but it's uniform everywhere. So this is the first big stumbling block, and it relates to the way that we are essentially reusing the functionality for fully unstructured meshes in order to mock up stretched grids. Ugh. I spilled all over myself in my Bill and Ted t-shirt. But let's dig a little bit deeper in here, because you'll note that we actually aren't using the unstructured mesh. We're using stream hexahedral hierarchy. And if we look at ds.index.grids 0, oh, it doesn't even have that. But the stream hexahedral hierarchy is not exactly the same. So if we look here, Stream, that's sample data. Unstructured mesh, index subobjects. You know what? There we go, unstructured mesh handler. So you'll see this doesn't use all of the same functionality. We've got this unstructured index. And now if we look down here, we also have, oh, maybe we don't. Let's see, where is our hexahedral mesh defined? Oh, stream hexahedral hierarchy. Okay, yeah. So you'll see right here, the stream hexahedral hierarchy actually does compute, or does function almost exclusively as an unstructured index. Oh yeah, look at that. Field info class. And it looks to me like the main difference is in the way that it knows how big the size is. So it will have meshes. So if we look at ds.index.meshes, it's got one. And that's a semi-structured mesh. So let's go look at our index subobjects. We've got unstructured mesh, and then we have a semi-structured mesh. And it's here that our I-coordinates are not generated. So let's see what happens if we do something like select I-coords here. And I'm going to raise a key error just so that we see where it is. I'm going to restart the kernel and clear all outputs. You know what? This is enough that I'm going to go ahead and just make a new notebook, because we're going to call this our rename notebook semi-structured index. Let's go back up here. I'm going to copy all the stuff that made our values. That should do it. Yeah. So now we should actually see a key error, if I'm thinking through this correctly. Yeah, we do get a key error. So here, if we are able to take our left edge and our right edge, convert that into a global start index of some type, then we can move forward to computing our actual I-coordinates and potentially even use our use this to get our projections working. Let's do mean of density along axis equals x. Let's see if this also gives us a key error. It does. Good. So you know what? Let's try doing something fun here. I'm going to go ahead and I'm going to split this, and over here in the right, I'm going to look at how our grid computes this. And here. So it's very similar to the way that we compute our selector masks and so on. Let's convert mask to indices. Actually, I suspect we are going to be able to do the exact same thing. Do we save our last count here? We do. If you haven't listened to AD by the Kleptones, I highly recommend it. That's what I'm listening to right now. Let's convert our masked indices up here. And you know what? Let me just go ahead and copy that out, and let's see what this gives us. Oh, yeah. We got to convert this into the right value. Let's see, does ds.index.meshes 0.get global start index not implemented? Alright, let's see. Restart and run all cells. Buffer has the wrong number of dimensions. Oh. Yeah, okay. Let's see. Okay, so we got this fill f widths. So I think we should be able to do np.where_mask. But I'm likely going to have to debug that to make sure that it's the right specific function. Yeah, it couldn't be broadcast together with shapes. All right. Import PDB, PDB.pm. Yeah, okay. It's going to be a little bit harder than I had thought. So let's I think we're going to have to do some Python here. So let's do that. I'm going to move unstructured mesh over to here, and then in this one, let's see, where do we actually do fill f widths? Okay, mesh utilities.pyx. Fill f chords. Let's see, that fills, it outputs in a one-dimensional array, which is not really what we want. So get selector mask for d-object selector. Mask comes back to us as an n-dimensional object. Fill mesh cell mask. So for the semi-structured, we also call fill mesh cell mask. Does this function the same as that one? All right, let's see if I can find go to definition. Of course. What am I, what? Or is it in a PXD file? PXI file? Okay. Selector object fill mesh cell mask. Yeah, so this is a very general process, because you'll see that it selects a bounding box based on whether or not that is included. So I think if we specialize this, I think we should be able to specialize this for our particular purpose, which would, and actually we should be able to specialize this a lot better than, okay, let's do it. Fill mesh cell mask, and here, fill semi-mesh cell mask. And what did we call this? We called it a mesh. Now let me comment this. This gives us our self, and let's see, which items do we usually access on this? We got position, blah, blah, blah. And really what we want is we want to come out with our IJKs. Hold on, might be able to do this a different way. I think we should be able to np.ravel index. What is the Ravel multi-index? I think I should be able to do Ravel multi-index of np.range 262144, dimensions of 64, 64, 64. unravel index. So this gives us what we're looking for. So let's take this. We've got our mask. We'll go back to our unstructured mesh, semi-structured mesh, where we compute the I-coordinates. So mask is equal to that. Now we'll say mask is equal to, so it's a little bit annoying, np.where mask. We don't have our dimensions, which is a little bit frustrating, so we will have to deal with that in just a minute. But for now, we'll just say that it's 64, 64, 64. np.unravel index, np where mask. So indices is equal to that. Just say 64, 64, 64. Mask equals np dot zeros. Dtype equals bool. Mask indices equals true. See if we can make this work just for our particular use case. Because if we can, then if we're able to pass the, okay, so ds.proj, ds.r, sum density axis equals x dot plot. This view onto it. What do we call it? These immutable attributes are a little bit irritating at times, but they are overall useful. So data set, no, static output. Mutable attribute. All right, so let's see if we can get at that somehow. ds.get, let's see. So let's just go back here. I mean, I'm really hacking the heck out of this. So let's go to data structures inside stream. Domain dimensions. Wait, do I just not set it? Loaders. Yeah, there we go. Just set it to 64. Now let me get rid of these cells where I'm working against it. Okay. set adder might have worked, but domain overflow, huh? That's load unstructured, load semi-structured, load hexahedral mesh. Let's see. I mean, ideally, what we're going to end up doing with all of this is specializing the semi-structured mesh code all the way down to having its own set of routines, which it's already neatly set out to do. Yeah, that doesn't look right. And the reason it doesn't look right is because we don't use F coordinates. That's right. So it works. Let's see. Inside our construction data arrays. Actually, don't want to look in doc. Tests, data objects, construction data containers. There we go. YT-proj. So here, you'll see that it does this RDX is equal to self.ds.domain-dimensions times self.ds.relative refinement. So that right there is the problem. It uses relative refinement in order to convert the integer coordinates back into floating point values. I suspect, oh, that's the covering grid, wait. Yeah, here we go, eye level. So this is where it does it. It does it in ds.iRes factor. That actually should have relative refinement included in it. The more I think about it, the more this is likely not going to be as hard of a problem as I had expected to convert this, because we've already got this eye coordinate stuff, the eye level, tree.add chunk to tree. So what we would need to do is maybe pull some of this method out into, I don't know, the data set or the mesh object or something like that. And then use that for the projections. But I think as is, we can already do slices and whatnot with this hexahedral connectivity. I'm feeling pretty confident that for data sets that utilize, that don't have overlapping data, so they're not AMR, but they do have different DX values based on where their position is. I think we should be able to do most of the functionality with YT as is using this load semi-structured mesh. Load hexahedral mesh. The next phase where we do this where we want to be able to do projections, it's going to take a bit of work, but I think as long as we don't do AMR initially, we should be okay. So I'm going to go ahead and stop my stream now, and I'll put this, let me make sure that this works, start to finish, and I'll do a gist of this and put it up on GitHub, and I'll link to that in the stream notes. So this should actually work without any additional data. Okay, I'm going to go ahead and stop the stream now, but I think that I understand where things stand a lot better. I hope this has been helpful.